Okay, now we are going to talk about the independence of three events. We will say that the events A, B, and C are independent if they satisfy all the following four conditions. And the first three conditions, if the first three conditions are met, the events are pairwise independent. They are basically the conditions we already saw for independence in the case of two sets. But we need the four conditions to say that the events are independent, okay? And this is the general formula. We will say that the events A1 until AN are independent if the probability of the intersection between them is the multiplication or the product of all the probabilities, okay? Basically, this means that the occurrence of or non-occurrence of any number of the events from that collection carries no information of the remaining events, okay? Let's see this example. Suppose a tennis player is practicing serves. She will serve 5 independent serves, okay? And any particular serve goes in with probability P. How likely is it that she will make the first 4 serves and miss the last one? So we can see this by, let's say, we have the probability of make, we can say make sub I is equal to P. We have that the probability to make the serve is equal to P. For I from 1 to 5, okay? And the probability, we have 5 serves. The probability of miss the serve I is equal to 1 minus P, the complement rule. This is the same for I from 1 until 5. The exercise is asking for how likely is it that she will make the first 4 serves and miss the last one. So the problem is asking for what is the probability of make the serve 1 and make the serve 2 and make the serve 3 and make the 4 and missing the 5 serve. So we have to calculate this probability, and we are going to use the independence condition here, because the probability of the intersection is the product of the probabilities if they are independent, and the probability of make the first serve and the second one is the probability of doing the first one times the probability of making the second one times the probability of making the third one times the probability of make the fourth serve times the probability of miss the 5 serve. And we will have that this probability is P, this probability, the second probability is P, this one is P, and the probability of missing the serve is 1 minus P. So this is P to the 4 times 1 minus P. Let's see this example. This is to make clear that pairwise independence doesn't imply independence. Consider 2 independent fair coin tosses and the following events. H1 is the first toss is ahead, the H2 is the second toss is ahead, and these the 2 tosses have different results. Okay, basically we also have here our sample space. Remember that is head head, head tail, tail head, and tail tail. We need to verify mathematically that the 3 events are pairwise independent, but not independent. So okay, let's check the first one. We need to check that probability of H1 intersection H2 is equal to the probability of H1 times the probability of H2. So what is the probability of H1? The first toss is ahead. Well, we have that this occurs in 2 events over 4, so this is 2 over 4. And the probability of H2 is the probability of that the second toss is ahead. This is in this element and in this element. So we also have 2 over 4. What is the probability of H1 and H2? Well, basically we will need that the first toss is ahead and the second toss is ahead. So we have 1 over 4. We need to check this, and 1 over 4 is actually equal to 1 over 4 in this form. So we have that they are equal. Similarly, we have to do that for the second probability. We need to check that the probability of H1 intersection D is equal to the probability of H1 times the probability of D, and same for the probability of H2 intersection D is equal to the probability of H2 times the probability of D. Well, this probability here is 1 over 2, is 2 over 4. Well, it's the same, 1 over 2 or 2 over 4, but to make clear, it's 2 over 4 times the probability of D. What is the probability of D? The two tosses have different results. So we have that this event and this event, they both form the event D. So this is going to be 2 over 4. And the intersection in this case is H1 intersection D. So the first toss is ahead and the two tosses have different results. So from these two elements on the square right, the only one whose first toss is ahead is this event over here. So we have that this is 1 over 4. And this actually holds again. This equality holds in this case. And we can also check, you can do this on your own to check the third pairwise independence. So now we have that all hold. So that means that H1, H2, and D are pairwise independent. But remember that for independence, for the full independence in the case of 3 events, for independence, we also need the probability of H1 intersection H2 intersection D. This has to be equal to the probability of H1 times the probability of H2 times the probability of D. And we can check this, that the probability of H1 we know that is 2 over 4, the probability of H2 is 2 over 4, and the probability of D is 2 over 4. But the probability of the intersection, that is, the first toss is ahead, the second toss is ahead, so that means we need the element HH, and the two tosses have different results. Basically this event here doesn't contain the element HH, so that means this is 0. So we have that these two probabilities are different. So this condition doesn't hold. So this condition so that means H1, H2, and D are not independent. They are pairwise independent, but they are not independent. Now, for the final example, we want to make clear that the equality that the probability of the intersection is equal to the product of the probabilities is not enough for independence. So consider two independent rolls of a fair seed-side die and the following events. A is equal to the first roll is 1, 2, or 3, B is the first roll is 3, 4, or 5, and C is the sum of the two rolls is 9. Okay, we need to verify this mathematically. The easy way to do this is by doing the grid diagram. So I will do this here. 2, 3. Okay, so basically what we need to do here is to check that this probability is equal to the probability of A times the probability of B times the probability of C. What is the probability of A? Well, the event A says that the first roll is 1, 2, or 3. So this is just about the first roll, and we have 3 elements. So the probability of A is going to be 3 over 6. We have 6 possible results on the first rolls, and the event A contains just 3 of them. And similarly, the probability of B is just the elements 3, 4, or 5. So we have 3 over 6. And the probability of C is that the sum of the two rolls is 9. So we will need the grid diagram to see this easier. So the sum of the two rolls is 9. It's going to be basically these points over here. They are 4 over 36 possible results. So this is 4 over 36. And on the left hand side, we have to calculate the intersection of these 3 events. Basically, the intersection between A and B, A intersection B, is just the element. This is equal to just the element 3, because the first roll is 1, 2, or 3, and the B is 3, 4, or 6. So the intersection is the element 3. So the intersection between A and B and C is that to have the first roll and number 3 and the sum of the two rolls 9. So the first roll we need a 3, and the sum of the two rolls is a 9. So in the grid diagram we have this 3 over here, and the sum of two rolls is a 9. So we'll need a 6 on the second roll, and this is just 1 over 36. And we need to check that this is equal to this 3 over 6 times 3 over 6 times 4 over 36. This is going to be 9 or 4 or 36 times 36. This is equal to 1 over 36. So this equality here holds for both sides. Now, remember that for overall independence, we need this condition, right? But we also need the pairwise independence. So we need to check, for example, the probability of A intersection B is equal to the probability of A times the probability of B, we will need all. Remember that for independence we need the 4 conditions, and we already know that this holds, but we have to check that all of the 3 remaining equalities also hold. So in this case, for example, the probability of A, remember that is 3 over 6. The probability of B is also 3 over 6. But we also saw that the probability of A intersection B, we calculate that was just the element 3. It was 1 over, it is just 1 over 6. And this is different than this. This is actually 1 over 4. So we have that equality doesn't hold. So A, B, and C cannot be independent.